If you want to build systems that scale to millions of users, you can't just treat the computer like a magic box that executes code. You have to understand the metal. Most people think performance bottlenecks only happen at the database or over a shaky network, but the truth is that latency doesn't just magically appear out of nowhere. It's born right inside the machines in the way your CPU fetches data and how your operating system manages resources. In this video, let us build a mental model for every performance discussion that we're going to have later. And before we design scalable systems, we need to understand why systems are slow in the first place. To understand why these systems slow down, we have to look at the physical brain of the machine, the component doing all the heavy lifting. So the CPU is where all the computation happens. Think of a core as an actual execution unit. More the core simply means that you can do more parallel work. A thread, on the other hand, is a logical unit of execution that the OS schedules onto a core. But here's the important detail. CPUs don't exactly execute hundreds of threads simultaneously. Instead, the OS rapidly switches context between them to give the illusion of multitasking. This context switching isn't free. Every time it happens, registers are saved, caches gets polluted, and execution stalls. The key takeaway here is that more threads do not equal more performance. In fact, context switching is the primary source of added latency. This brings us to a hard truth. In production, your CPU rarely struggles with math itself. The real bottlenecks come from chaos of managing that work. In real world systems, CPUs don't usually hit a wall because the math is too hard. They hit a wall because of management overhead. We call this the CPU saturation. It happens when too many threads are competing for too few cores. When threads are constantly blocked, waiting for the input or the output, or fighting for the access to the same resources, the OS has to work overtime just to keep track of all of it. And that is called thread contention. Instead of doing the productive work, CPU spends its time on scheduling delays, trying to decide which thread gets a next turn. When context switching overhead dominates your CPU cycles, your throughput tanks. This is exactly why phrase just add more threads is almost never the right solution. It's often like trying to put out a fire with petrol. You aren't adding more power, you are just adding more chaos for the OS to manage. And that's why it is said that more threads is not equal to more performance. Now, a CPU can only process data as fast as it can get its hand on it. To understand why even a powerful CPU can end up sitting idle, we have to look at the memory hierarchy. In your head, memory might just be RAM, but in system design, memory is a hierarchy optimized for one trade off: speed versus size. At the very top, you have registers. These sit idle in the CPU itself and are accessed in a single cycle. Below that is cache. They're small but incredibly fast pools of data. Then you have RAM, which is larger but significantly slower. And at the bottom, we have the disk. It's massive, but compared to the CPU, it's painfully slow. To give some intuition on the numbers, access times for cache are measured in nanoseconds. RAM takes about 100 nanoseconds, but the disk, that takes milliseconds. That might not sound like much, but a millisecond is 1 million nanoseconds. Every time the CPU looks for data and it's not in the cache, what we call as a cache miss, latency explodes. If the CPU has to wait for the disk, it's essentially standing still for an eternity in computer time. If a millisecond feels like an eternity to a CPU, then we need to take a closer look at what happens when CPU is forced to wait. This is where high-level system design meets low-level physics. Modern CPUs are incredibly fast, but only if the data is nearby. When the CPU finds what it needs in the cache, it's a cache hit, and things move at light speed. But when it misses, it's called a cache miss, and the core experiences a memory stall. It literally stops working. It sits there doing absolutely nothing for hundreds of clock cycles while it waits for data to arrive from the slow RAM. This is exactly why high level system design decisions ripple all the way down to the hardware. It's why data locality, that is, keeping related data close together, is so critical. It's why your choice of caching strategies and your memory access patterns can make or break a system. When you design databases or an API, you aren't just moving JSON, you're managing how often your CPU is forced to sit idle. If you ignore the hierarchy, no amount of clean code will save your performance. We've looked at the memory layers inside the machine, but most of our data lives long term on the disk. And when it comes to disk storage, not all hardware is created equal. When we talk about persistent storage, we are looking at two completely different worlds: HDDs and SSDs. Hard disk drives are mechanical, they rely on spinning platters and physical moving heads to read data like a record player. This mechanical movement is a massive bottleneck. On the other hand, we have solid state drives, which are flash based with no moving parts. That single difference itself changes everything for your system architecture. An HDD operates in milliseconds, whereas an SSD operates in microseconds. In the world of system design, simply replacing HDDs with SSDs can give you a 10x to 100x improvement in latency, all without changing a single line of code. If your database is slow, sometimes the fix isn't a better algorithm, it's better physics. But to choose the right hardware, you need to know how to measure success. You'll often hear these three terms used interchangeably, but mixing them up is a recipe for slow system. In performance tuning, there are three metrics you'll often hear constantly: latency, IOPS, and throughput. They're often confused, but they measure very different things. First, latency is the time it takes for a single operation to complete. This is a wait time. Second, IOPS stands for input output operations per second. It basically measures how many small tasks can we fire off in a single second. And third, throughput is a raw volume of data flowing through the pipe, like megabytes per second. Here is a vital part for system designers. A system can have massive throughput and high IOPS, but still have terrible latency. You can move a lot of data at once, but if each individual request takes forever to respond, your users are going to feel it. Remember, users don't feel throughput. They don't care how many million operations your server is doing in the background. They feel the latency. If you optimize for the wrong metric, you might build a very powerful system that feels painfully slow to the person using it. Now we know how hardware performs, but how does the software actually organize itself to use these resources? This is where operating system draws the line between processes and threads. To keep the system stable, the operating system uses two main units of execution: processes and threads. A process is like a complete isolated container. It has its own dedicated memory space. If one process crashes, it doesn't take the rest of the system down with it. The memory isolation makes the processes very safe, but it also makes them heavy. Switching between processes is expensive for the CPU. Inside a process, you have threads. A thread is a lightweight worker. Unlike processes, threads inside the same process share the same memory space. This makes them much cheaper to create and switch between, but it comes with a dangerous trade off. Because they share memory, they can easily step on each other's toes, leading to those nightmare concurrency bugs and race conditions we all deal with. Most high performance systems like modern web servers or databases carefully balance both. They use multiple processes for isolation and security, and multiple threads within those processes to maximize speed. It's a delicate dance of both safety and efficiency. Even with the perfect mix of processes and threads, your system's real speed is determined by how it handles input and output. This is the difference between a server that waits and a server that works. One of the biggest choices you'll make in system architecture is how you'll handle input and output. Generally, you have two paths: blocking and non blocking. In blocking IO, when your code asks the disk for a file or the network for a response, the thread literally stops. It says, stop everything until the operation is finished. This is simple to write, but it's incredibly wasteful. Your thread is consuming memory and context switching overhead while doing absolutely nothing. Non-blocking IO changes the game. It tells the system, start the operation and let me know when it's done. Meanwhile, I'm going to do another work. High-scale systems avoid blocking wherever possible. Why? Because block threads are graveyard for performance. They waste CPU cycles and bloat your memory usage. Understanding this is the foundation for everything we talk about in modern tech, from asynchronous servers and event loops to reactive systems. If you want to handle 100,000 concurrent connections, you can't afford to let your threads just sit around waiting. Now we've optimized the CPU, the memory, and the input output model, but we need one more layer: the organization of data on the disk itself. This is where the file system becomes the bridge between your code and the storage hardware. The file system is our final abstraction. It's what turns raw chunks of binary data on a disk into something we can understand: files and dictionaries. But here's the thing many engineers overlook: accessing a file isn't about reading the bytes. Every time you open a file, the OS has to perform metadata lookups to find where that data actually lives. It has to check inodes, verify permissions, and traverse directory trees. All of this adds overhead. File systems design directly impacts your system's performance in ways you see every day. It determines your startup times, it dictates how fast your logging system can flush to disk, and it ultimately ensures your database durability. If you don't respect the file system, your high level application will always be held back by the way its data is organized on the metal. But what happens when you run out of physical metal? When your application needs more RAM than the machine actually has? To handle this, the OS uses one of the most powerful and dangerous tricks in the book: virtual memory. So, virtual memory is a genius abstraction that lets every process believe it has its own massive private memory space. The operating system manages this by breaking memory into chunks called pages. It maps these virtual pages into physical RAM. But here is where things go south. When your RAM runs out, the OS doesn't just crash, it starts swapping. It takes those pages of memory and moves them onto the disk to free up space. Suddenly, your memory access is actually a disk access. If you remember our memory hierarchy, we're talking about falling from nanoseconds to milliseconds, a million fold slowdown. This is catastrophic event for latency. The key takeaway here is that out of memory problems often become latency disasters long before the system actually crashes. If your server suddenly feels like it's running through molasses, don't just look at the CPU, check your page faults. You might be swapping your key into the performance nightmare. We've covered a lot of ground in this video and it all leads to this. Latency isn't an accident, it's the result of physical and logical limits. Latency exists because hardware has physics, like CPUs have to wait on memory, memory has to wait on the disk, and threads have to wait on the network. On top of that, the operating system is trying to manage thousands of competing demands and it schedules everything imperfectly. This is the most important lesson for any architect. Every system design decision you make is an attempt to work around these fundamental limits. When you implement caching, you are fighting the memory hierarchy. When you use asynchronous APIs, you are fighting input-output blocking. When you implement sharding or replication, you are trying to bypass the limits of single machine CPU and disk. You cannot design a scalable system if you don't respect the metal it runs on. So now that we have looked under the hood, why does this matter for high-level diagrams we draw every day? From this point forward, every advanced topic we discuss in this series is going to rely on this foundation. When you talk about why a cache helps, you will know it's about avoiding 100 nanosecond RAM penalty. When we discuss why async matters, you will visualize threads not being wasted while running an IO. When we talk about databases, you'll understand why sequential disk access is your best friend and random access is your enemy. I'll see you in the next video. Thanks for watching.